All right, so this is third period, and today is Thursday, the 11th of March. I'm going to read this to you. This is something that you had in your notes from 2 days ago. It says, radioactive dating, technique in which scientists calculate the age of a sample based on the amount of remaining radioactive isotopes it contains. All right, that's a term from Unit 6. We're going to talk about that. All right, we're going to talk about that, but put a pin in that for a moment. All right, so let me kind of get you up to speed, and this may take a little bit of following my train of thought here, but we're in Unit 6, and that is the history of Earth. Okay, the events that our planet that we call home has gone through. All right, so big picture, the Earth is approximately 4.6 billion years old, with a B, billion. Okay, our Milky Way galaxy is 13.8 billion, just to put perspective on it. But let's just talk about Earth, all right? So in 7th grade, thus far, that means until now, we have discussed some of the processes that take place on our planet, again, what we call home. The seafloor spreading, moving continents around, okay, pushing continents in different directions and remapping where the continents are. Now, keep in mind that the continents move at about the same rate as our fingernails grow. You ever had to trim your fingernails? Okay, it's not, all the time you have to do it, but turn around like, man, my fingernails are getting long. The continents are actually moving at about that same rate. All right, so when you think about it in like our lifetime, let's just say 100 years, it's not a great deal. But if you think about it in big picture time, like tens of thousands, millions of years, it tends to be a lot. All right, so we're going to kind of jump around a little bit, but let me kind of remind you. This is a globe, and it has where we call our 7 continents as we know them today. All right, so to put things in perspective, let's go here. I'm going to make this lens a little different so you can see it. All right, so here we are in Florida. Let's just follow my finger here, all right, just to give perspective. This is where we live in Florida, all right? We move up through the North American continent, through all the different states till we get up here to Alaska, all right? And then we keep going to the edge, the west side of Alaska. Let's say you were right here. If you were geographically right here today, you'd be standing on dry land, and you'd be looking at what looks like an ocean, okay, going due west. And if you got into a boat, and you went due west, it wouldn't be too big of a voyage, but you would arrive to more dry land. And you would be on the continent of Asia, all right? So following this, down through Asia, over here to Africa, where my finger is, more or less, this is the continent of Africa, and what we call modern day Botswana, okay? A spot geographically in Africa. Here's the reason I bring that up. We will be talking about evolution, right? Like how things evolved, including ourselves, all different types of, animals. And by the way, animals, okay? We are in the kingdom Animalia, all right? So there's this whole thing that 6th graders will learn soon. 7th graders have already learned it, okay? It's called Linnaean taxonomy. Kingdom, phylum, class, order, family, genus, species, all right? I will review that kind of stuff with you guys as we go. But just to kind of mention it a little bit, we, humans, okay, are in the same group as a dog, a rabbit, a mouse, animals, to be animate and full of life. We are breathing out carbon dioxide, we're taking in oxygen. I'm going to get to that in a moment, but let's just say that early humans, okay, people, our ancestors, let me revisit some things I've taught you before. I have parents, you have parents. Your parents have parents, their parents have parents, their parents have, and we can just keep going. If you go back far enough in that time frame, going back generation after generation after generation, you realize that we have what you call ancestors, okay? People who we are genetically related to. We are here because a set of people reproduced, and they reproduced, and they reproduced, all the way to your parents reproduced, and here you are, here I am. All right, going backwards in early human history, all right, there are, we're Homo sapiens sapien, thinking wise man. That's a scientific name for us, the people that we are. But there are other species that are no longer around, they are extinct, of early ancestors to us, okay? And we can go back to, like I said, modern day Botswana in Africa. There was a group called the Australopithecus, and there was a couple of subgroups, Australopithecus afarensis, Australopithecus africanus, and eventually what was happening is that they were following, these early ancestors were following migrating animals, That might have been blurry. I think I had the lens wrong. Sorry if it was blurry. They were following migrating animals. So watch my finger here. Let's just say, and I will tell you a little story very quickly. There is a scientific study underway following the mitochondrial DNA, which is passed from mother to child, that traces our ancestry back to this spot geographically on the planet. That is modern day Africa, all right? So let's say early humans, let's go back 200 million years ago, were wandering around following food, because back in those days, make sure the lens is not, sorry. Back in those days, there was no, supermarket or McDonald's or anything of that nature. It was literally hunting for survival, for what they call subsistence. You needed to find food in order to survive. Now, a little review from 6th grade, you are learning about prokaryotes and eukaryotes, or not 6th grade, prokaryotes, eukaryotes. We are eukaryotic organisms. We are complex organisms who must consume nutrition in order to have our processes take place that allow us to be alive, okay? So we eat food and we get energy from it. Well, when you are a hunter, you have to hunt food to provide for yourself as well as any family you might have. Okay, so we'll get to a story here in a minute, but let's just say this. People early on were following food, following migrating animals that were traveling. So these herds of gazelle and gemsbok, and later on in the Americas, buffalo, things like that, were traveling, were herding, migrating, okay, and hunters were following them. Now let's go all the way up here into Asia, and let's go back to where I said this little spot was here. So if you were here 10,000 years ago, just 10,000 years ago from modern day, there would not be a body of water separating this continent to that continent, okay? The body of water was not there because the sea levels were lower. And when the sea levels were so low, it exposed the land that's now underwater, making this thing called a land bridge, the Beringeal land bridge. So our ancestors followed the migrating, herding animals across that land bridge, right? Now going back to this. So what happens is a lot of people say, "Oh, this is good. We like it here." And some of the people said, "No, we're going to keep going." So you get like little settlements, little areas where people stayed and settled. This is North America. They worked their way down through the Isthmus of Panama down to the South American continent, and you get all these little settlements of individual people, which later became, after long-term evolution, later became what we call races of people. You develop where geographically where you had adaptations for survival. So if you were in a place that had high equatorial solar exposure from the sun, you developed darker skin. If you were in windy environment, you developed an epicanthic eye fold. All right, we'll get to all that in genetics, but the story is early people were hunting food. Okay, now let me tell you a story here. Let's just say that this guy, he lived, let's put a date of 25,000 years ago. He's the man. He is a more evolved human. He's not Australopithecus afarensis. He is Homo habilis, the tool man. He gets that name because Homo habilis didn't figure out how to make screwdrivers and sockets and hammers, that kind of tool. He figured out how to use rock and break it into pieces to make sharp edges for bows and arrows, for spears, fishing hooks out of bones. More importantly, fire. By hitting two rocks together, two flint rocks, it created a spark, and with the right conditions, you can get fire. Homo habilis figured out quickly that fire was something that animals were afraid of, so they used it as a protective tactic for things that might be a predator, like lions and tigers and leopards and things like that, to keep them away, but also to hunt. So here's what they would do, and there's evidence of this. They would use flame and fire to scare usually a small juvenile, like this case here, it's one of those woolly mammoths, related to an elephant. They would push that animal to the edge of a cliff and then eventually get the animal to fall, and then gravity would do the dirty work. So let's just say that this hunter is out with his son, who doesn't seem very threatening, but he's just kind of watching his dad do his thing with the fire, and they push this unlucky animal down here, okay? Animal breaks its leg or dies on impact. If it breaks its leg, they go down, they kind of finish it off. So now let's say that animal is now dead, knocked the tree over, and the family of this man, okay, this is like, let's call her the mom, comes down and makes the fire and makes a basket, while the daughter goes and collects material for the basket. Because again, if you're a hunter or gatherer and you find things, you got to take it with you because you keep on going. All right, so you're wandering around and you got to bring things with you. So they would make things like baskets. But the point here is that you've got a dead woolly mammoth and you've got a fire. All right. Now, over a long period of time, wind and water is going to move and erode this material here and cover it, all right? So this will all be covered, layer after layer. So let's go ahead and do that. Let's look at this. So now, this would be like where this woman was standing 20,000 years ago, but it has now been covered, so it's actually, you know, thicker. The material is built up, and it's actually layer upon layer upon layer. And if you go down far enough, there's the remnants, the remains of that fire. There's the skeleton. Now let's say you are a paleontologist, you know, a person who studies fossils, or an archaeologist looking for early people's artifacts, and you dig down and you find this site, and you're like, ooh, I've got charred, burnt wood. That means it might have been a fire. Well, I've got, you know, an animal right next to it. It means that somebody probably, you know, cooked this animal. There's a way that you can figure out how old something is based on the number of carbon-14 in that material. Let's talk about that. Going back to you and I being animals, and or a dog or a guinea pig or a turtle or anything else that breathes air, they're breathing out carbon dioxide, all right? They call that carbon-12. You don't have to know this, but it's because there's 6 protons within carbon-12. There's 6 protons and 6 neutrons. 6 and 6 is 12, all right? So the story is, let's just use a cow. It could be anything. It could be us even, but let's just say an animal is breathing out CO2, carbon dioxide. Again, we're going to call it carbon-12. As the animal, or us here in this room, are breathing it out, the gases in this room it mixes with, it homogenizes. So in this room, there are carbon dioxide and oxygen and xenon and fluorine and carbon monoxide and miscellaneous gases all in this room. And as those gases work their way out, they meander out. Every time we open the door, works its way outside out of the building, cars going by, making a lot of current, make the carbon-12 that left our mouths work its way up into the upper part of the atmosphere. Put a pin in that. I'm going to read this to you, all right? Carbon, CO2, carbon dioxide, or carbon-12 hooks up with neutrons, 2 to be more specific, in the upper atmosphere, adding 2 neutrons from gamma rays, making carbon-14. We remember from the electromagnetic spectrum unit, gamma ray is very short, powerful wavelength, okay? Gamma rays come from stars, and in the upper atmosphere, the carbon-12 hooks up with the neutrons from the gamma rays in the upper atmosphere, giving it 2 more. So 2 plus 12 is 14. That's why they call it carbon-14. Carbon-14 is radioactive. Now, radioactive material, there are many, all right, but they have an isotope to them. And so that's what this particular piece of information that you have in your notes represents, is that radioactive material has an isotope. Carbon-14 has what they call a half-life. All radioactive material has a half-life. It means that in a certain amount of time, half of the material divides in half and the other half converts to something else. We'll just talk about carbon-14 right now. All right, I'm going to read this to you and then I'll explain. Radioactive dating, 5,730 years. The half-life of carbon-14 is 5,730 years. This means that every 5,730 years, carbon-14 converts to nitrogen, leaving half of the original amount. All that means is, let's say that, and let me go back to us respiring and whatnot. We have, you and I, we have carbon-14 in our body. We do. Every living thing does. Now let's say you're this paleontologist and you find, this site here. Ooh, what's this? Oh, it's a mastodon. You'll find something that's got more or less the same makeup, okay, the same body mass, like an African elephant, and you'll measure the amount of carbon-14 in that specimen, all right? So that gives you like a base to say, all right, this is modern day, this is how much carbon-14 is in an animal that's alive today, and you look to see how much carbon-14 is in the animal that you found the remains of, all right? So you can compare it. All right, so here we go with this. Let's assume that this is a whole sample, all right? It's a whole sample, it is today. So let's just say, like I said, this is from an elephant. Okay, and we're gonna compare an elephant to the mastodon. All right, so today, all right, that's a whole. If you were to cut that in half, just think of fractions. A whole, if you cut that in half, gives you a half, right? So we'll just kind of do that. This might take me a minute to do this, but here you go. So there you go. We had a whole, we cut it in half, all right? Then let's say we cut it in half again. We're just talking fractions now. So we have a half. Well, I should have wrote it over here. I don't want to be confusing. Let me do it here, over here. So half, okay. Quiet back there. Now let's say we cut half in half again. That gives us a quarter. So that's just fractions, right? Pretty basic. And then let's say we cut that in half. We cut a quarter in half. That would be an eighth. Okay, again, just basic fractions. Okay. Oops. Okay, now, here's how this goes. I'm gonna do something, I hope it works out. I'm gonna put this here because I can't hold the camera and do this at the same time. I kind of want to show you guys not only how to do this, but also like a math trick. It's kind of cool. So early people, the earliest form of writing that we know of was in a place called Mesopotamia, and that's modern day Iraq. So like where Iraq is today. And so the Mesopotamians, they were really called the Sumatrans and the Akkadians. They were Suma. That's what they were. They were Suma, but they were, you know, like we're Floridians. They were Sumerians. But anyway, they're pretty advanced, and they gave us a lot of things that we carry over to today. And we've learned about time. If you were in my class not too long ago, we learned about, you know, how the rotation of the Earth and how that relates to time. They had this system because they came up with the way that how many degrees are in a circle, 360, how many seconds are in a minute. You ever wonder, why is it 60? Why isn't it 100? Or why isn't it 80? They would do this kind of, you know, trick, let's call it. Remember, it was 5,000 years ago. With their thumb, they would touch every crease of their fingers, of these 4 fingers, and count. And I'll show you how they did it. So to come up with like 60, they would say, like, they use their thumb and they go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When they got to that finger, they'd hold up 1 on this hand. So this hand kind of kept track of how many times you got to 12. So then they do it again. But they keep going from 12. It's 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and they'd hold up another finger. They keep going, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, hold up another finger, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, hold up another finger, and then the last 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. And then they'd start over. So that is where the whole 60 minutes, 60 seconds, 60 minutes, you know, the whole thing about time came from them. But let me show you how this math works, you know, towards this problem. Okay, I hope you can see this. Okay, so we said, let me just kind of move this for sure so I know you can see it. We said 5,000, where is it at? 5,730 years, okay? Let me do this. This is a different way of doing math, and you can do big numbers, because I always hated, like, you know, when you do, like, when the numbers get big, like, how many zeros do every column you have, like 3 zeros, 4 zeros? When you do big numbers, it gets ridiculous. But you can do it like this. You can go 1, 2, 3, 4, 5. That's the 5 here. Now we're going to do the 7. Kind of make a space. 1, 2, 3, 4, 5, 6, 7. Make a space. Do 3 for the 30. 1, 2, 3. And the 0, you just kind of make like a long oval. I think you guys can see that now. I'm just moving the camera so you can see it. Okay. So then, you can do it with the same color, but it kind of stands out a little bit better with a different color. So 5,730 years, this material today in 5,730 years would divide in half, okay? I know this might seem confusing, but it's very basic. You have a hole, all right? And in 5,730 years, half of it becomes nitrogen and leaves the other half. And in another 5,730 years, half of that becomes nitrogen and just leaves half. And then in another 5,730 years, the same thing happens. And it keeps going, all right? So it'd be like a whole, a half, a quarter, an eighth, a 16th, a 32nd, a 64th. Eventually you get to where there's nothing left to divide. So you arrive to a point where you cannot accurately date material that's so old. But here's the math, all right? So let's say we know that today if we did this once, 5,730 years, you'd have that amount. Well, what would that number be? All right, now you could do a calculator, and it's pretty easy to do on a calculator, but doing it out on paper is definitely a skill to develop. But let me just show you how this works. So this represents 5,730. Let's put a line through it, like one, all the way down. And I'll try to hold it and show you as I do it. If it touches this zero here, it is zero, okay? So you just make zero. And I always put a line under it because a line means it stays put, all right? And I'll explain that as we go. Now this one, the line goes through these three, so we just count how many times it goes through. 1, 2, 3, put a 3. When I said if it stays put, it's because it's in the ones place. If it's in the ones place, it's not gonna move. If it's in the tens place, it'll move, and I'll explain that here in a second. So this one, how many times does it go through? 1, 2, 3, 4, 5, 6, 7. So it's in the ones place, so put a line under it because it doesn't move. This one, 1, 2, 3, 4, 5. Okay, ones place, doesn't move. Then you would just kind of like copy it. We'd say 5. Yeah, this might seem a little trivial here for the beginning, but it does, you know, make more sense as we get into bigger numbers. Okay, so there you go. Now let's do it for if it happens twice. All right, so that number 5,730 we just assigned to this spot because today that's a whole. In 5,730 years you have half. All right, now let's do what happens if it happens again. That's another 5,730. All right, so now if it touches the zero, it's always going to be zero, so you just put a zero. Okay, now here let's count 1, 2, 3, 4, 5, 6. It's a single digit, so it's going to stay. Put a line under it. This one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's a double digit, so you write 14. The single digit stays. This one carries up, so we just put plus 1. Now up here we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 plus 1 equals 11. So that stays. Now we just copy it down. We say 11. And then this is the underline here. We say 4. Basically whatever's underlined. 6, 0. Okay. My handwriting's bad, sorry, but 11,460. Now what happens if we do it times 3? And again, we can go times 20. You can literally just keep going with this. So times 3. We'll stop at that. So because it's touching 0, put 0. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a ones spot, so it stays. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 has, tens location, so we underline that. We're going to carry this up and just say plus 2. And then we're going to add it to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 plus 2 is 17. Copy that. 17. 1. 9. 0. Okay, put your comma in. All right, so let's copy that over here. So we said 11,460. 11,460. We said 17,190. 17,190. Okay. Now, a question could be asked of you. All right, if you have a whole sample that is 40 grams of carbon 14, how much will you have in 5,730 years? You would say, okay, well in 5,730 years, it's going to cut in half. Half of 40 is 20, okay? I would have 20 grams. If the question said, if you have a whole sample of carbon 14 that is 40 grams, how much would you have in 11,460 years? You would say, all right, well, and that's what I have now. In 5,730 years, it would cut in half. And then in 11,460 years, that would be cut in half, giving me a quarter, all right? So what is, well, let me start over here. a whole, a half, what would a quarter of 40 be? Would be half of 20, which is 10, all right? So just to keep things straight, a whole, we cut it in half, we have 20, which is just dividing that by 2, then we divide that by 2, that gives us 10. If I even went even further for advanced, and I said, if you had a sample of 40 grams, how much would you have after 17,190 years? You would say, all right, well, starting here, it would go 5,730, I would have 20 grams, 11,460, and I have 10 grams, and at 17,190, half of 10 would be 5 grams, all right? So that is the step to figuring out how you come up with the age versus, or comparatively to the carbon-14 found in a sample, how old it is. And again, there are limitations with this because you can only go back so far before, if you divide it in half over and over again, eventually you have nothing left to divide. All right, so then there's another method that uses another material called uranium. And I'll try to set my camera up for you here. Give me a moment. Uranium has a half-life of 4.5 billion, with a B, years. That means that in 4.5 billion years, half of it converts to something else and only leaving half of the original sample. Now, this is something that I will show you. Get the lights out. Okay. All right. Here we go. There was something that in the 1930s was kind of cool, and they call it uranium glass. Uranium glass. And it's sand that's melted down to make glass, and there was really beautiful, trinkets and things that people had in their homes, cups and pitchers that were made from this. And the reason why they called it uranium glass is because it actually had uranium in it. And nowadays, there are people who kind of make their living going to antique shops or flea markets and things like that looking for this stuff because it's quite valuable. And they always have a little pen with them that shines in the electromagnetic spectrum called black light, UV light, okay? And they go and they shine it on glass. And if it glows green, everybody see that? Can you see that from where you're at? If it glows green, it has uranium, all right? So what that means is that in 4.5 billion years, this won't glow green. Of course, nobody will be around, but nonetheless, this material, okay, will have a half-life of 4.5 billion years and not glow green at that time. But the point is that uranium is what gives us the approximate age of Earth, because uranium has a half-life of 4.5 billion years. Now, we say Earth is 4.6 billion years because there has to be Earth to have uranium. So that means that if there's uranium that's got 4.5 billion year age to it, well, Earth has to be at least a little older than that. So they say 4.6 billion, all right? So the take-home message with that is that there are techniques that allow science to use these radioactive dating materials to put a date, an absolute date to certain material, all right? Rocks, once living organisms, remains of once living organisms. Okay, so that is our lab for today. I will give you some questions that go along with this, and spring break is almost here. Tomorrow's the last day. Yes. Any questions? No? All right. Okay, here we go.